Okay, here we are. This is the 3.1 we're talking about now, and there's some applications using our derivatives. First thing we want to talk about, well, I have to say most of the chapter, better part of it is devoted to analyzing behavior of functions and their graphs. So first several sections, up to I believe 3.6, deal with just graphing and analysis. So let's get started. Extrema. We have a technical definition here. There is a minimum at C. F of C is a minimum. If the value there is less than all other values around it, okay, and an interval I. Okay, all and an interval I, and likewise it's a maximum if f of C is greater than any other value of the function. We also call these absolute extrema or absolute maxima, absolute minima. Okay, now every continuous function, we can go into some detail in this minute, but every continuous function on a closed interval must attain a maximum and a minimum. Okay, so that has to happen. It has to have it. Now, relative extrema, these are points that are not absolute, but they are relative to a confined neighborhood of the point. They are high points and low points, extrema. So, for example, you might see a graph that looks like this, and in this region here, this is a low point, but it's not the lowest point. Here's the lowest point right here. So relative to this neighborhood in here, this is a minimum. Likewise, over here, this point is a maximum, but it's only a relative maximum because notice over here, you have an absolute maximum. Okay, so now all extrema are considered relative, but only certain of them are considered absolute. So now, we can fill in these blanks here. If there's an open interval containing C on which F of C is a maximum, then F of C is called a relative maximum. Okay, and if there's such that F of C is a minimum, then F of C is called a relative minimum. Relative minimum. Okay, now, seeing that this is an open interval, relative extrema cannot occur at the endpoints. Okay, like for instance, if this is my function here, and it just stops there and stops there, and it's just open interval, then I can't have a relative extrema right there on the ends for this end. Okay, so relative extrema are not going to occur on the ends unless it's a closed interval. In that case, we might have a relative extrema. Okay, let's continue. Critical number. We'll get to some problems in a minute. Let's see. Let's just write critical number. Graphs. Oh, okay. Let's just go straight to the definition. Suppose F is defined at C. If if f prime, and then it's a little smudge there, but that's the derivative of f prime. If f prime of c is 0 or not differentiable. Okay, in other words, if the derivative is undefined right there at c, then we call this a critical number. But it has to be a point on the curve. Okay, it has to be a point there. If we have f prime equals 0, then we have a critical number. Or if f is undefined there, sorry, non-differentiable there, then it's a critical number also. So let's talk about finding some critical numbers here. Let's do one example. Call quits on this first video. Okay, so find the critical numbers. Well, we have to find the derivative. Prime of x. Okay, so critical numbers means you're going to be looking for f prime. Now, f prime, we got a quotient here. We need the quotient rule. So we have 4. That's the derivative of the numerator times the denominator, minus the derivative of the denominator times the numerator, all divided by denominator squared. We'll simplify this a little bit. So we have 4x squared plus 4 minus 8x squared. X squared plus 1 squared. And then we get the denominator in that form. This becomes a 4 minus 4x squared over x squared plus 1 squared. Okay, so once you have this derivative, you set it equal to 0. Well, you can see I can ignore the denominator because this will only be 0 if the numerator is 0. Okay. Now, we'll check the denominator in a minute, but for right now, the prime is 0 there. Notice they're not 0 in the same place. Denominator is never 0, actually. So, okay, so set the denominator, set the numerator to 0. See this, and this will be true of x as well. Okay, now, so these are critical numbers. All right, now you can check, is it undefined anywhere? Okay, so we checked, where is it 0? Got those. What about undefined? Check that too. Well, that would happen in this case. Here's my derivative function here. That would happen if the denominator, for this particular function, if the denominator became a 0. Well, that's not going to happen because this quantity will not be 0 for a real number. So there are no critical numbers resulting from an undefined derivative. So these are the only two that we have right here.